Hello, students. Welcome to Module 2. We will start talking about the physical layer. We are roughly going to devote a week to this layer. I want you to be aware of the fact that people make careers out of physical layer, studying the physical layer. We call them PHY engineers. They are the ones who major in telecommunications. And this is the layer that deals with taking a signal from your laptop, from your computer, from your cell phone, and sending it over either air, if it's a wireless communication, or over a guided medium. And by guided medium, we mostly mean wires, or through satellite. So physical layer deals with the physical transmission of data from point A to point B. Lots and lots of issues in this layer that has to be dealt with and addressed for the seamless delivery of data from your machine to the recipient's machine. Okay, so keep that in mind. It's just because we're devoting a week to this does not mean this layer is not important. This is super important. Since this is a computer networks class, we tend to focus more on the higher layers, and we have courses that are dedicated. You'll see the communication courses, the digital communication, the analog communication courses that are dedicated to just this layer. So that was my kind of disclaimer that I don't want to be disrespectful to this layer because we are devoting the least amount of time to this layer. But with that introduction, let's move on and see what the physical layer is about. The other instruction that I have for your advice or suggestion that I have for you is you might find the textbook loaded with a lot of information, and some students find it overwhelming. For this particular layer, you'll see my slides very wordy. Normally, I tend to go very cryptic on my slides. The purpose is that you just pick up the topics and the gist of the topic, and then you refer to that section in the textbook for a detailed reading or understanding of the material. In this particular module, my physical layer slides are really wordy because I mostly want you to get most of the content from the slides itself. Okay, so however, do feel free, and for those who are advanced and have some knowledge in this area, the Tannenbaum textbook does a wonderful job bringing forth the different topics to you. So go ahead and indulge yourself with the details if you so choose. But for the purposes of the exams, in this particular course, what I cover in the slides and in my lectures are pretty much what you'll be expected to know in terms of knowledge from this layer. Okay, so with that, moving on. Okay, so it is the lowest layer of any network protocol stack. Okay, the lowest layer of the OSI reference model. We in this course, as I have said in my previous lecture, we are going to be focusing on the 5-layer hybrid protocol stack. So this is the lowest layer of the protocol stack. We call this layer 1. And in the commercial world, in the professional domain, you often hear people using the term, he's a 5-layer guy, or he's a 5-layer engineer, or he's a layer 1 engineer. So this is what they're talking about. It's abbreviated as PHY. And as I said, this is the layer where data physically moves across the network interface. So what do we mean by the network interface? So say, for instance, when you're typing an email, you type an email, you hit the return key. When you hit the return key, your email is in English language, right? When you hit the return key, guys, I'll use the example of your laptop. In your laptop, the operating system of your laptop has the layers of the protocol stack, code written to represent the layers of the protocol stack. That email is composed in the topmost layer of your network protocol stack, which is the application layer. When you hit the send button, the operating system of your machine calls upon the different functions layer by layer, the transport layer function, the network layer function, the data link layer function, and finally your physical layer function. And then once each of these layers have done their job on the email that you composed, on the data, so the data here is the email that you have composed, on your email, it then, by this time, your data, your email is not that English language email that you composed anymore. It is now signals, zeros and ones, or electromagnetic waves, which leaves your machine into the medium. And again, I repeat, the medium can be wired or wireless, okay? The network interface is exactly that. It's that boundary which allows your data to leave the machine and enter the physical world, okay? So you can imagine this is a very, very important layer. The role of the PHY, this is, a lot of words. What I'm saying here is a lot of times people think PHY layer is about the network cables, but it's not just that. It's a lot more than the network cable. There are algorithms that are implemented on the data to make sure that the receiver, when it receives the data, can understand whether the data was received correctly or not. So that's what I'm saying here, that hardware equals PHY is not accurate, okay? Functionalities. So PHY, and this is something, this slide is important, guys. It tends to show up on the exam. I kind of tend to give you these functionalities and ask you whether they are, true or false, whether these functionalities belong to the PHY layer, things like that. You'll see that in my practice quizzes. So definition of hardware specification. What kind of, so say for instance, to give you an example for this one, look at the cable. So right now, see, I have this power cord, okay, which is attached to my laptop, and this is charging my laptop, okay? So look at the thickness of this wire, okay? The thickness of this wire, yeah, I hope you can see this. The thickness of this wire, compare that to the thickness of a cable that's laid below the oceans to carry data from, say, North America to Australia. Do you think it'll be the same? Hopefully your intuition is telling you that it won't be the same. And why will it not be the same? Because the amount of data that's moving through those cables, the kind of reliability, the distance through which that data will be moving are different, right? So who decides what kind of connectors, what kind of network interface cards, what kind of hardware, meaning kind of cable, would we need to get the data through? It's the physical layer, okay? It also determines the physical layer, so I'm moving on to number 2. Physical layer also determines the encoding and the signaling. It's responsible for the kind of, as I said, the data protection in some way, just so that the data can travel the distance that it needs to travel, and it has enough information in it just so that at the receiver end, the receiver is able to at least say whether this data was received correctly or not, okay? So say when you're saying, so when you speak on the phone and you say hi, and your friend hears a ho, there has to be some way for the friend to understand, or the friend's phone to understand, that ho is not an English word. Chances are the caller wanted to say something else. So that's what we mean by, the encoding and the signaling. It's not just that spoken word or the email that's sent, it's padded with a lot of extra information for these purposes. Okay. Data transmission and reception. So at the interface, so when the signal leaves the device, so that email is now a signal. When the signal leaves your device and when the signal enters the device, the first layer that it encounters is physical layer. And again, I repeat, and I'll be repeating this throughout just so that you have it in your brains, that all this protocol stack that we are talking about, okay, this is software, this is code, computer code, mostly written in C language, which exists in the operating system of any machine that's capable of communicating to the outside world. Okay, so keep that in mind. So when the data enters a machine, the first layer it encounters, and then what do I even mean by the first layer it encounters? So if layer is software, what is actually happening? What is happening is the operating system calls on a function, the PHY function. The function executes its functionalities on this piece of data that has just arrived. Okay, so that's what we mean when we say the data transmission and reception part. The interface is managed by this physical layer. The topology and network design, how big the topology is. Last chapter 1, we talked about LANs and WANs and MANs, bands. So the physical layer is also considered the domain of, so it makes the determination of what the network topology should look like, because the farther a network spans, the connections, the kind of wires we need, the kind of signaling we need, the kind of encoding we need, all of this changes. Okay, so it's the physical layer that makes these determinations. So this is an important slide, guys. Do look it up from the textbook, read in a little more details. You can read this on your own. Okay, so issues to consider at the PHY. The parameters that we are talking about, so what are the things, what are the decisions that the PHY makes? Which frequency to broadcast on, so these three, which modulation scheme to use, and what error correction detection mechanism to use. So I'll tell you later on what we mean by the first two. At the data link layer, we'll talk a lot about the error correction detection part, okay? Transmission medium. So what kind of medium to use? Okay, so the transmission medium may be guided, wireless, or satellite. Okay, now if it is, you understand wireless, we use it all the time. The guided medium is the cables. Okay, also remember this, guys, that even when we call a network a wireless network, so say for instance we have cell phones, wireless, right? The phones are not connected to a cable for the data to travel, only the last hop. So data from your cell phone, whether it's your text message, whether it's a phone call, your cell phone wirelessly transmits the data to, most of the time, a master switch, which your cell phone provider. So if you're subscribing to AT&T, if you're subscribing to a T-Mobile, that traveling of the data from your cell phone to a cell tower, okay, that hop is wireless, the nearest cell tower. Okay, so your cell phone has the ability to detect where the nearest cell tower is. So the cell tower is almost like, think of it as a router that you have at home for your Wi-Fi. Okay, that hop is wireless. Your cell tower most of the time is attached through cables to a master switching center, again provided by your service provider. Okay, a lot of times it may communicate using microwave links, if it's a point-to-point and depending on where that cell tower is situated. But mostly, roughly speaking, cell tower onwards, it's again a wired network. Okay, does the cell tower have a physical layer built into it? The answer is yes. As I said, any device capable of communicating with any other device has to have the protocol stack built in it. And when I say built in it, code has to be written. The protocol stack is software, it's code, it's functions. Okay, if you have written a C program, just the way your main calls different functions to execute different tasks, that's what I mean when I say your operating system calls these functions in a sequential order in order to execute, get your data ready for transmission. So each of the layers that we will be going through in this class, think of them as a function call in a big program. Okay. So the choices that we are making about whether it should be a twisted pair, whether it should be a multi-pair cable, whether it should be a coax cable, whether it should be optical fiber, depends again on the kind of network we are trying to connect, the devices that we are trying to connect. How far are they? How much reliability do they need? All transatlantic, transpacific cables that connects data from North America to the rest of the world are mostly optical fibers. They have very high reliability. Okay. Also, remember that it's a signal, right? So when data moves through this guided medium or even through air, the data degenerates. We use the term attenuation. So the signal attenuates, meaning the signal decays. Okay. Now, if the signal decays, we need to do something to revamp the signal, pour energy into it just so that it doesn't die down. Okay. And the analogy that I like to use oftentimes is, say, for instance, because I'm talking to a computer right now, and the computer is like a few inches from me, there's only so much energy that I'm putting into my voice, right? So when I'm putting in this the amount of energy that I'm putting in right now, it's enough for the computer to grasp my words. If I were to deliver the same lecture in a classroom, I would throw in more energy, more power in my voice when I'm throwing out my words, right? So the signal is exactly like that. However, there's a physical limitation to how much energy I can throw in my voice, right? So what I mean by that is, even when I'm lecturing in a classroom and I have the capability of speaking louder or throwing in more energy in my voice or words, my voice can probably carry through the student who's sitting in the last row of a decent sized classroom. Okay. However, I am incapable of throwing in energy to a point where I can be heard 5 classrooms down the aisle, right? However, if my recipient, if my student, if my class is so big that my voice does need to reach 5 classrooms down the hallway, what do? I boost my speech. How do I boost it? So in the domain of this transmission medium thing, this repeater spacing, the last column, this repeater repeats the signal. It's almost as if someone is sitting in classroom 2 repeating what I just said. So they hear what I said. They don't need to understand networks. They just need to be able to speak English, hear what my words are, repeat my words. And that repetition is good enough to carry that voice to classroom 2. At the end of classroom 2 and beginning of classroom 3, there's yet another person installed who repeats what he or she heard from classroom 2. And when she repeats, classroom 3 can hear the same words that I spoke in classroom 1. Okay, so that's the job of a repeater. So if you look at this, in an optical fiber, it's okay to place a repeater 40 kilometers. Okay, but in a twisted pair, you have to place a repeater every 2 kilometers. Okay, so the signal dies down much faster. So now you can get a sense that if you're carrying signals below the ocean in a cable, you cannot. It's an expensive proposition to be repeating the signal every 2 kilometers, right? So you'd rather use a medium where the signal does not need to be repeated for at least 40 kilometers. Okay, so that's so what do you need? What should you be taking away from this? What you should be taking away from this is this comparative understanding of your optical fibers can carry your signals longer distance without being repeated, whereas your twisted pair cannot. Your coax does better than a twisted pair, but much worse than an optical fiber. Okay. In an exam, I'm not going to ask you for these numbers per se, but I would expect a relative understanding that a twisted pair is good enough for your laptop to be attached to your power cord or your projector. An optical fiber is an overkill there. but a twisted pair is not adequate to be carrying your data below the ocean. Okay, so that's what I expect from you, an understanding that I expect from you from this slide. Okay, electromagnetic waves. So as I said, when the signal, your email, your voice, when it leaves the device after all the different layers of the protocol stack has acted upon it, it's no more the English language. It's a signal. A signal is a wave, and therefore this electromagnetic wave. If it's a digital signal, it's zeros and ones, but it's still voltage, and it's still, it's a square wave, but it's a wave. Okay, so what are electromagnetic waves? When electrons move, they create electromagnetic waves that can propagate through space, that can move through space. These waves have energy. They are called electromagnetic radiation. And these waves can be created in different ways. There are natural waves. The sunlight is, again, packets of energy, photons that comes to us. That's a wave. And then there are man-made electromagnetic waves, like the TV waves, the microwaves, the radio, remote control, your garage door opener. These are all waves from this device to the final destination device, which is instructing that destination device to execute a specific task. All these waves taken together is called the electromagnetic spectrum. Okay. Again, the analogy that I like to give, and maybe I'll wait for the next slide. I'll come back to these. Look at the electromagnetic spectrum, guys. Okay, so this electromagnetic spectrum, the way I want you to think of the electromagnetic spectrum, or let me just say, I don't want to rephrase that. When I first learned about the electromagnetic spectrum, what helped me understand it was thinking of the electromagnetic spectrum as a freeway. So envision that freeway is a roadway through which cars can travel. So my cars are my electromagnetic waves. Okay. Now, just the way the freeway has lanes, and roughly speaking, the right lane is for slower moving vehicles and the left lane are for faster moving vehicles. Similarly, the electromagnetic spectrum, which is the freeway, is divided into lanes. And in each lane, we have a certain kind of wave that can traverse through that lane. And what kind of waves? Roughly the same analogy. Some waves can travel fast. Some waves can travel slow. The ones who travel slow probably reach a longer distance. The ones who travel fast can't reach or are obstructed or absorbed by brick walls and trees. So the lanes in the freeway has designated properties which enables certain kinds of waves to travel through those lanes. But the collection of all those lanes together forms the electromagnetic spectrum. Okay, that's my cell phone, guys. If you can hear it, just ignore it. What you're seeing in this slide is exactly that. What you're seeing is different kinds of waves. Look at this kind of wave, guys, versus, so when you see this, look at how this wave looks versus how this wave looks, okay? And come back to this to see, now, read the line that I have here. Radio is the name given to, radio is the name given to the electromagnetic waves that can be used for communication. Okay, what do we mean by that? Think of X-rays, guys, and I think you'll see X-ray somewhere right here. You'll see X-ray here. Okay, so X-rays have a wavelength of 10 to the power minus 10 meters. Okay, whereas the 10 to the power minus 10 wavelength wave looks something like this, the picture right beneath it. Okay, the gamma ray, which has a wavelength of 10 to the power minus 12 wavelength, looks something like this. And we'll speak in a bit about what a wavelength is. And radio waves, okay? What are radio waves? The waves that we use to communicate, send data. And these are the waves that your garage door opener uses to open your garage door, your TV remote control uses to operate your TV, your cell phone uses to send out your text, your voice, so on and so forth. So any wave that we can use for communication is called radio wave in the common lingo. So radio waves roughly have wavelength 10 to the power 3. So those waves look something like this. They are, you know, much more spread out. Okay. So let's go back to, so this is, as I said, the collection of electromagnetic waves. Now, waves have properties. The three particular properties that we want to look at: wavelength, frequency, and amplitude. So wavelength, what is wavelength? It's the length between two consecutive peaks of an energy wave. They can be as long as 10 to the power 6 meters at the bottom of the spectrum, or as short as 10 to the power minus 15 meters at the top of the spectrum. And wavelength is denoted by this Greek word lambda. Okay. So the wave, in my opinion, any two consecutive points, okay, on a wave is a wavelength. So from a peak to a peak is easy to measure. From a trough to a trough is also wavelength. Okay, so between two consecutive peaks of an energy wave, as I said, radio waves, longer wavelength. As we go down that spectrum, as you know, you're moving to the left of the lane, the wavelength gets shorter and shorter. Okay. Frequency, the next property of the wave. What is frequency? It's the number of times, number of complete cycles a wave makes in a second. Okay, so we just learned about wavelength. So see, from here to here, say it's one wavelength. Now let's say, look at this. In 1 second, so if we freeze time, in 1 second, how many complete waves does a particular wave make? How many complete cycles does this particular wave make? So in 1 second, if a wave completes one cycle, okay, then the wave completes one cycle per second. This cycle per second is measured in a unit called hertz. Okay, so there are waves that can make 10 to the power 3 complete cycles in 1 second. 10 to the power 3 complete cycles in 1 second is referred to as kilohertz. 10 to the power 6 cycles per second is referred to as megahertz. The longer the wavelength, the lower the frequency. Okay, and then give this sentence a thought. The longer the wavelength, okay, so you saw longer wavelengths 10 to the power 3 meters, right? So the longer the wavelength in 1 second, how many complete cycles does that long wave make? Much less. If your wave looks like this, the number of complete cycles this particular wave makes in 1 second will be a lot more. Okay. So frequency and wavelength are inversely proportional. And that inversely proportionality, the constant of that inverse proportionality is c, which is the speed of light in vacuum, 3 to the power 3 times 10 to the power 8 meters per second. I have corrected this God knows how many times on my slide, and it still comes down to this, and I don't know what's wrong. So it's not 3 times 108 meters per second, guys. It's 3 times 10 to the power 8 meters per second. Okay. Lambda F equals C, very important formula. Okay. Something that you should keep in mind. Okay. And there could be simple questions about this lambda F equals C in the exam. So keep, I might give you, you already know C, I might give you the F, and I might ask you to find the lambda, or other way around. You know C, I give you lambda, find F. Okay. Okay. And then amplitude. Amplitude is the measurement of the height of the wave. So it's also a measurement of the strength of transmission. Higher the amplitude, the stronger the signal. Okay, so it's almost like the amount of energy that you're throwing into your voice. Okay, the more energy, the higher the amplitude in the signal. Okay, and I show you here what the amplitude looks like. So we have wavelength, we have amplitude, and then we have one complete cycle. Okay, and then comes the electromagnetic spectrum, which we already spoke about. So why did we study this wave thing, guys? Because, as I said, the physical layer is throwing out your data into the medium, not in the form of your English language email, not in the form of your English voice, English words spoken as voice, but all of this data is taken and then transferred to represent a wave. Okay, so therefore it's somewhat important to understand what a wave looks like, what the properties of the waves are, because a lot of this defines the exact choices that we spoke about. What kind of transmission medium needs to be used? I very deliberately avoided the word frequency when we were talking about the transmission medium, because we hadn't visited what frequency is. If you go back to that slide of transmission medium, you'll see, let's do that. You'll see that every transmission medium supports a certain frequency range. So a twisted pair supports frequency range of waves between 0 to 3.5 kilohertz, whereas an optical fiber can support waves of frequency 186 to 370 megahertz. Get it, guys? What does it mean to have a wave which is 186 to 370 megahertz? That means it's making 186 times 10 to the power 6 complete cycles in 1 second. So think of the speed at which it moves, okay, as opposed to the twisted pair. Okay, so the medium, and again, an analogy here, guys, is think of the hose, the pipe that you attach to, say, your garden tap. Okay, what you do in your backyard, tiny garden, my garden is tiny, so the backyard tiny garden, I'd probably use a hose which is like, this narrow. A farmer who plants trees and has acres and acres of agricultural land probably will not use a hose this narrow. Right? So the gush of water that can go in through this hose to water my 10 plants, this is enough. But if I need to be watering 10,000 plants, I'll probably need a bigger pipe which can gush out water at a higher speed. That's exactly what's going on when we talk about the frequency range. Okay. So that's why we need to have some idea and information on the properties of the wave so that we can make these decisions intelligently. Okay. Also, things like, see, the higher the frequency, guys, of a wave, they get absorbed by walls, trees. So that's why we cannot use a wave in this frequency range to communicate data. Our wireless waves, when your email leaves your laptop and travels for the access point in your house to be picked, for it to pick up your email, that wireless travel, that travel through the air, you have furnitures, you have staircases, walls through which your data is traveling before it reaches the access point. That wave moves through space, right? And it's not free space. Your wave needs to be able to penetrate these objects and keep moving. A wave in this frequency range, such high frequency range, gets absorbed. And that is why X-rays have what they have. We use X-rays to get the images of our bones. Why? Because most our bodies will absorb the ray, the light, and it'll not reflect back. Okay. The radio waves are waves that can pass through these objects, and that's why it can be successfully used for transmitting data. Okay, so it's important to know a little bit about these properties, otherwise we cannot make informed and educated decisions of transmission mediums to use. Okay. Bandwidth, a very important term, but a term used slightly differently amongst different people of different expertise. So in the network domain, bandwidth is almost always, a lot of times bandwidth and throughput are the same. So I give you a pop quiz. What's the difference between bandwidth and throughput? I really want you to look this up, either from the textbook or from the internet. And so in the network domain, guys, bandwidth often refers to data measured in bits per second. So whenever someone asks you what is throughput, throughput is data by time, amount of data in unit time. That unit time can be second, minute, hour. Okay. So, and data is mostly bits, megabits, kilobits. Okay. So 50 megabits per second. That's my throughput. If you look at my definition of bandwidth, I'm pretty much saying the same thing. It's data measured in bits per second. So the bandwidth in the network context often is synonymous with throughput. Not so in the communication domain. For PHY layer experts, its bandwidth is not throughput. Bandwidth is the difference between the upper and lower cutoff frequencies of a filter, a channel, or a signal spectrum, typically measured in hertz. Okay. What do we mean by that? A signal oftentimes probably is not, it does not have the same frequency all the time. So it might be a very, a close up and down, and then spreads out a little bit, and then a more up and down. You must have seen, how heart rate is monitored, patients in hospital. You see these in movies and TV series, right? So that signal does not have the same frequency as I showed you in the previous slide in my electromagnetic spectrum. So for communication people, for physical layer experts, bandwidth is the difference between the upper and the lower cutoff frequencies. Okay. And it's measured in hertz. Okay. Channel capacity. This is very important, and for sure there'll be an exam in the for sure there'll be a question on the exam asking you to measure, to find out channel capacity, either using the Nyquist formula or the Shannon formula. And make sure you know how to do this. Okay. I believe I know I have posted some numerical problems on Canvas. So check them out. I have samples of roughly the questions that might show up on the exam. So first of all, what is channel capacity? It's going back to my garden hose analogy. If my hose is this big, okay, what is the amount of water this hose can carry? If my hose is this big, what is the amount of water that my hose can carry? Okay, so the amount of water that my hose can carry is the capacity of the hose. And that's exactly what we are after. We need to know when your ISP promises you that you'll get data, 50 megabits per second, how are they promising that? Yeah, a lot of things go into play in determining what the throughput that a user will experience. One of them definitely is the transmission medium size. So two scientists, first Nyquist, who tried predicting MDR stands for maximum data rate. Okay. And again, what is data rate? Rate at which data is being sent. So anytime you use the word rate, guys, it's always per unit time. So some unit of time. It could be, again, seconds, minutes, hours, what have you, but per unit time. So, and maximum data per unit time, okay, that this channel can send through. Okay. So for a noiseless channel, so Nyquist proposed this long time ago for a noiseless channel, that the maximum data rate can be found with this formula. And this formula stands for 2 times, H represents hertz, so the frequency of the signal, LG stands for log to the base 2. Log to the base 2 is represented as LG instead of LOG. LOG stands for log to the base 10. So LG is log to the base 2, and then V. V stands for the level of the signal. So if it's a binary signal, you have a 0 and a 1. Okay, so your signal looks like a 0 flat, and a 1 goes up, spikes up at a certain level. So if you have a 2-level signal, like a binary signal, your V value of your V is 2. Okay, the frequency is normally given to you, and make sure that the frequency if it's a megahertz or a kilohertz, convert it into hertz. Okay, so H is hertz. So 2 times hertz log to the base 2 level of this times level of the signal, bits per second. Now, noiseless channel is the catch here, guys. Most channels are not noiseless. So what is noise in a channel? And again, you learn a lot about these things when you take a communication class. What is a noiseless channel? A noiseless channel, guys, is, so say for instance, wireless. In wireless, as I said, I'd like to see air as that freeway with these invisible lanes through which my signals are traveling. Now, because it's air and it has dust particles, it has water particles. If it's raining, then it has a lot more water particles. If it's snowing, then it has snow. Now, all these water molecules, snow molecules, dust molecules, they're moving around. Every time they move around, they are creating noise. They are clashing against my electromagnetic wave that I'm sending through this airspace. So to my wave, all of these particle movements is noise. Okay. Similarly, in a wire, so you would think there is no air, snow, dust in a wire. Well, there is no vacuum anywhere, right? So air has particles in it too, even in a wire, and those particles move. And again, they clash with my electromagnetic wave that's going through the wire. So those air particles moving through the wire is noise to my signal. It attenuates my signal. And I have to take that into account. Nyquist did not take it into account. He couldn't, but when he proposed this, he didn't have the means to do that. We still study his formula because he showed us a way to get there. And then Shannon came in, and Shannon is considered, Claude Shannon is considered the father of digital communication. He gave us this super famous formula to relate maximum data rate of a noisy channel, okay, which is the reality. All channels are noisy. So the maximum data rate of a noisy channel with SNR is signal to noise ratio is H again stands for frequency measured in hertz, log to the base 2. Log to the base 2 of what? 1 plus S over N. Okay, so S over N is the raw signal to noise ratio. Okay, so this quantity is the maximum data, and it's in bits per second. It's the maximum bits per second that a particular channel with this frequency can carry, which has this signal to noise ratio. So understand, guys, your signal has to be really strong. And so when your numerator is a big number and your denominator is a small number. So say, for instance, your numerator is 100 and your denominator is 10. Okay, so that's what is 100 divided by 10? 10, right? However, if your numerator is 10 and your denominator is 100, what is that number? 0.1. So it's a much smaller number, right? So for a number to be big, the numerator has to be a bigger number than the denominator. So here too, if your signal has to reach the destination, the noise cannot overpower it. So you are looking for a signal to noise ratio where the numerator has to be much larger than the denominator, or should be larger than the denominator. If the denominator is much larger than the numerator, your signal will be drowned. However, in the communications world, guys, for the most part, we do not measure raw signal to noise ratio. We use this thing called decibel, and in a decibel, what we do is we use this ratio called signal to noise ratio, and in signal to noise ratio, the relationship is, so when we say a channel has a signal to noise ratio of 100, or say a 20 dB, not 100, 20 dB. So 20 dB stands for 10 times log to the base 10, the raw signal to noise ratio. So the raw signal to noise ratio, if you think about it, if the raw signal to noise ratio is 100, so 10 times log 100. Okay, so log 100 is 10 to the power 2, right? So log 10 to the power 2 boils down to 2. So 10 times 2 is 20. So 20 dB. So when we say that the noise is 20 dB, what we mean is the raw signal to noise ratio, the raw S over N is 100. And in Shannon's formula, it's the raw S over N value that we need to plug in. So always remember that. So you need to remember that dB means when we say that, there's SNR is 20 dB, we are not speaking of the raw signal to noise ratio. We need to use this in order to find out what the raw S over N value is, plug that in here, and then do the math to calculate the MDR, Shannon's channel capacity. Okay, so my next slide has a couple examples. Your textbook walks you through a couple examples. Try it for yourself. If you don't understand, send me an email. Okay, and I can help you walk through this. I also believe I have examples of this in the practice problem set. Okay, modulation. So the next topic that we'll visit is called modulation. It's the process of encoding source data onto a carrier signal. The source data can either be analog or digital. The carrier is always an analog wave. So let me give you a layman's analogy of what modulation is. Say, for instance, guys, when I speak in my cell phone or the communication protocol cannot force me to speak in a certain way. By that, what I mean is cannot force me to throw in a certain amount of energy into my voice. Okay. Now, so I will be speaking the way I want to with as much energy as I want to. My energy in my voice pretty much governs the shape of my signal, right? And then different people speak differently. When my voice enters the cell phone, and the cell phone has to transmit it through the hidden antenna. You don't see the antennas on your cell phones anymore. Just a second. Anymore. So when the cell phone has to transmit this signal through the antenna, there's a certain dedicated, as I said, a path on the freeway, a lane on the freeway, which is designated for this particular signal to travel on. Now, why this designated path? This designated path because you have paid money to AT&T. When you pay money to AT&T to carry your signals, AT&T has gone and bought a path in this wireless spectrum from the government, paying billions of dollars. So the airspace which AT&T is using to transmit your signal hasn't come for free. Okay. Now AT&T has to transmit all its clients' data on that path. So it's almost like saying, Toyota bought the middle lane of the freeway from the government. Now, a Toyota Corolla, God, I don't even know the other models of the Toyota. Toyota makes, Okay, so it has bought, let me just change my story a little bit. It has bought the middle lane from the government. The government has this restriction that in the middle lane of the freeway, all cars traveling in the middle lane of the freeway can travel no less than 50 miles per hour and say no more than 80 miles per hour. Now, Toyota cannot force all its drivers to comply because there are drivers who are just learning. They probably are scared to go at 50 miles per hour. There are old people who probably cannot do the 50 miles per hour, right? So what Toyota does is it has its own vehicles which are guaranteed to travel at 50 miles per hour. What they will do is when they see a vehicle that cannot move within this prescribed range, they put these cars on these vehicles that are guaranteed, that are Toyota's vehicles that are guaranteed to move at 50 miles to 80 miles an hour. And you have seen trucks, right, which carry a lot of cars. So think something like that, okay? So I'm piggybacking a driver's car onto a 50 to 80 miles per hour car, just so that I am adhering to my rule so that I can use that lane to carry my car through. Modulation is exactly that. A signal has to move in a certain frequency band. The original signal may not be of that frequency. Because as I said, waves are created in different ways. How do you force that wave, or how do you enable that wave? Not force, it's the wrong word, too negative. How do you enable that wave to traverse that frequency band on which it's supposed to traverse? And why that enforcement of that it has to traverse that? Because as I said, it could be your laptop, which is using Wi-Fi. All signals in Wi-Fi has to go through 2.5 to 5 gigahertz range. It could be your cell phone data, which depending on the subscription that you have, if it's an AT&T, it has a certain band in air that it has bought. If it's a T-Mobile, it has a certain other band in the air that it has bought, frequency band, and all their signals has to then cater to that frequency band. So then, guys, the only option that you have is have this carrier wave, which will adhere and comply to the requirement of the path, the frequency requirement of the path, and you piggyback your own data wave onto the carrier wave and carry it along. Okay. So that technique of piggybacking is what modulation is. Piggybacking a source data onto a carrier signal. The source data can either be in a digital format or an analog format. The carrier wave is always analog. Extremely important technique. And there are different forms of modulation. It's good to know some of the terms here. Taking digital data, making it into a digital signal, digital data, analog signal, analog data, digital signal, analog data, analog signal. And, you know, the analog AM, FM, analog modulations, okay? Nyquist sampling theorem, this is something good to know. The way I look at it, guys, is feel free to read this section up from the textbook or even from the internet. I send a wave out from my device. The receiving device receives the wave. So what does it mean to receive a wave? There are bursts of signal energy impinging on the antenna of the receiver wave. Okay. The antenna may not be constantly absorbing all the pulses. The frequency at which it takes in this incoming energy determines how accurately it can reconstruct the original signal. Now, if it's not sampling or looking at the signal closely enough, okay, it may not be able to reconstruct the signal. However, constantly scanning, being able to take that energy is a lot of power. We want our systems to be efficient, what is the minimum frequency at which you can be looking at the signal, which enables you to reconstruct the original signal? That's what the Nyquist sampling theorem is. So it says if a signal f of t is sampled at a regular interval of time at a rate higher than twice the highest frequency of the signal, then the sample contains all the information required to reconstruct the original signal f of t. So this sampling at a rate higher than twice the highest frequency of the signal is important. Okay. Again, let me give you an analogy for this. As you're going through my video, guys, just by nature of how the human mind works, probably none of you are latching onto every word that I'm speaking. Okay. Now, some of you maybe you started with a lot of energy. This video is probably more than an hour long. Initially, you were paying attention and you were probably holding on to every word that I was speaking. And then your attention waned. And then every 5 minutes, your mind is wandering. You're coming back. You're listening again for the next 5 minutes. Your mind is wandering again. For some of you, it could be 10 minutes. For some others, your mind is wandering away for 15 minutes. So the more your mind wanders away, guys, and if you're coming back to my lecture every 5 minutes, every 15 minutes, every 30 minutes, think of the information that the student who's coming back every 5 minutes is gathering versus the student who's coming back every 30 minutes is gathering. The student who's coming back every 3 minutes probably has enough information to understand the content of this lecture, I would say 98%. The guy who's coming back after every 5 minutes probably has enough information to understand the content of this lecture, 90%. The guy who's coming back after every 30 minutes probably has enough information to understand the content of this lecture, no more than 10%, if that, right? It's exactly that. How often are you looking at the signal for you to be able to reconstruct the signal back? Okay, so why are you not constantly looking at the signal? Well, you are not constantly latching onto every word I'm speaking because your mind is wandering, and that's how our human minds are. For a circuit, it's just not power efficient. Okay, so we want to find the minimal amount of time, which is enough to reconstruct the signal back. Okay, and that's what Nyquist sampling theorem gives us. Okay. Multiplexing, this is our last topic. Multiplexing is, channel space is important, guys. Channel is, be it wire, be it wireless. We seldom send out one signal on one wire. Especially think of the transatlantic cables that I'm talking about. Think of your own homes, guys. You probably if you're living at home, mom, dad, brother, sister, you, 5 people. Mom, dad, you, minimum 3 people. If you're living with roommates, 3 roommates, 4 roommates, at least minimum 2 roommates, you and the other guy. Okay. Both of you on your laptops using Wi-Fi, you have one router. You are shooting emails, he is shooting emails, you are watching Netflix, he is on YouTube. Both your data, 802.11, the government, 802.11 is the standard for Wi-Fi. Okay. And you should have read about the standardization process in the last chapter 1. So 802.11 is a standard body that the government created to regulate, to standardize protocols so that this Wi-Fi, this wireless local area network, can be used by every vendor all across the world. Okay, so when you shooting out emails and your roommate watching a YouTube video, both your data traversing that same 2.5 to 5 gigahertz lane in the freeway of air. Okay, because that's what Wi-Fi spectrum is. Now, in that lane, it's subdivided into 13 channels. Okay, each of those channels, so that one of those 13 channels, America, I believe, uses 11 of those 13 channels. Each of those channels, guys, in a university setup, guys, think the ECE building, electrical computer engineering building. The top floor, the Wi-Fi router that we have, it's tuned to receive data on just one of those 13 channels. The second floor will be programmed to receive data on another of those 13 channels, just so that there's no clash. You and your neighbor might be using the same channel, okay? And that's slightly problematic, but we can't help it because there's no synchronization. There's no one guy who's setting up your whole neighborhood, okay? That way, each one of you would have used a different channel. But now coming back to you and your roommate, chances are both of you are using, say, channel 1. So if both your data are on channel 1, how does the router understand that this is data from Bob and that is data from Jill? And Bob and Jill's data coming to me on the same channel, but I'm still able to differentiate them. That is what multiplexing is about. And the channel, so your physical layer, the channel multiplexes it, and then your router should be able to demultiplex it, meaning separate it out again. Okay, so that process is what multiplexing is. And my last slide is about the different kinds of multiplexing. There are a lot more than this. Frequency division and time division are the two classical ones. You have 3 different signals which you modulate. Remember modulation, piggybacking. You modulate on 3 different carrier signals with 3 different frequencies. You club these 3 modulated signals onto this one channel, okay, passing through this 92.0 to 92.6 megahertz frequency band. And then you have filters, which filters out. So it's almost like 1, 2, 3. This combination, you put a filter through which only this part filters out. These 2 are left behind. So this filtered out signal, that's a bandpass filter, it then goes through a demodulator, it separates the carrier wave from the data wave, and you have your data signal back. That same combination of 1, 2, 3 wave now is passed through a second filter. The second filter filters out 1 and 3, retains 2. Again, that same composite wave passes through the third bandpass filter. That filter is designed so that it can retain 3 and filters out 1 and 2. Okay, so that's how you get your 1, 2, 3 modulated signals. You then pass them through demodulators, which separates the carrier wave from the frequency, from the data wave. Okay, and then you get your source waves back. Time division multiplexing is you give each of your user a certain amount of time to send their data. So, and you create a frame, which is a composite frame, which has chunks of data, each coming from a different source. So say, for instance, your frame is 3 seconds long and you have 3 users. First second is for user 1, second second is for user 2, third second is for user 3. Okay, so your 3 second long data frame has data which is 1 second long from 3 different users. So it's that pattern is written in stone. So at the receiver end, you know exactly which second to pick up in order to understand who that data came from. Okay, so that's how you multiplex. Again, the whole point is channel is an expensive resource. You just don't want to have dedicated channel for one conversation. You want to be putting several conversations on a channel just so that you can make the maximum out of it. So that pretty much brings us to the end of that is all the topics that we want to cover in this course on physical layer. Go through the slides, pick up the sections from the textbook, which talks about these content. Some of them can be a lot more than what I spoke about. For exam purposes, you'll roughly be responsible for the amount that I spoke about and spent time on. From this chapter 1, from this module 2, PHY layer, what shows up on an exam, transmission medium, what is multiplexing, what is modulation, Nyquist and Shannon formula, being able to calculate maximum data rate using those, wavelength frequency, lambda f equals c, roughly these ideas. Okay, so make sure you're picking the right topics, looking them up on the textbook, and reading them up to get a good understanding of it. That, along with the practice problems, you should be good. Okay, so have a good one, and I'll see you in module 2. Bye.